Testing gives confidence by example. Formal verification gives certainty by logic. Instead of running a million inputs hoping to find the edge case, you describe the property you want. Total supply never exceeds 1 million. And let the move prover feed every possible state, path, and adversarial input into an SMT solver. If the solver says valid, the property holds for every future block. If not, it returns a counterexample you can reproduce. The prover sits in the same CLI you already use, meaning bulletproof guarantees are one flag away. Move's spec language feels like a cousin of Daphne or JML. You attach declarative rules right next to your code. Preconditions describe required inputs. Postconditions promise how outputs change. Invariants are always true laws on storage. Need to express every element in this vector as unique? Wrap it in a for all. Need to reference the supply before minting? Call old total. The syntax is lightweight, and because it lives inside the same .move file, the rule evolves with the code. Once the spec blocks are in place, verification is a single command. The CLI compiles the package, translates specs into logical formulas, fires them at the Z3 solver, and streams results. Success prints a satisfying green banner. Failure pinpoints the exact rule and provides a concrete state where it breaks. From there, you either tighten the code or relax an overzealous spec. Specs map to typical finance rules: supply caps, balance conservation, monotonic IDs. Some hazards, like reentrancy, die at compile time thanks to Move's borrow checker, so you seldom need a spec. For the rest, write a line or two. The prover does the grind. We attach two invariants to the module. The first is obvious: total never breaks the cap. The second shows off quantifiers. There exists a vector of every point on chain whose amounts sum to total. You don't materialize that vector, the prover reasons abstractly. If a future dev forgets to increment total in Mint2, the second invariant will fail, breaking CI long before mainnet users mint unaccounted points. For functions, you assert what must be true afterwards. Our mint to postcondition states new total equals old total plus amount. If code increments by amount times 2 or forgets to update at all, the solver finds the mismatch. You can help the prover by sprinkling by blocks, tiny proofs of sublemmas, but 9 times out of 10, the engine figures it out. The spec sits inside the function body in its own spec block. All identifiers in scope are usable. Old sup.total captures the pre-call value. Run SUI move prove. If both conditions hold, a green badge appears. If you comment out the code line updating subtotal, the prover instantly flags the failure. Proofs can take seconds to minutes. In CI, you can skip unchanged modules for speed and run a deeper, more exhaustive pass overnight. When proof fails, the solver dumps a JSON counterexample. Exact variable values, abort code, and path. Attach that artifact to the failed job so developers reproduce locally. The prover isn't omnipotent. Infinite loops or cryptographic proofs require manually supplied loop invariants or abstractions. And spec design is like API design. If you hardcode balance equals 42, version 3 will never raise the cap. Write intentions, not incidental numbers, and remember, deleting a failing spec to make CI green is like smashing the fire alarm to stop the noise.